Hi, everyone. We are at NeurIPS 2024 Fine Tuning and Machine Learning Workshop. I'm Farris, and this is my coworker, Yahya. We are from Mercedes-Benz in Sunnyvale, California, and we work on a variety of tech topics there. At that office, we were the first car manufacturer to integrate ChatGPT into our cars, and we're extending that now by integrating language models on device in production cars. So let me walk you through how we enable that. Um, our problem statement is that we want to enable language models for function calling in vehicle, and the functions we want them to trigger are interior vehicle functions like seat heating, ambient lighting, the AC, etc. But a lot of language models out of the box, they're too big and too resource heavy to actually execute. So we need to do things in the meantime to actually make them feasible to run on hardware. So our recipe for this is pruning a language model in two different directions before deployment. The first direction is depth-wise pruning. Uh, the Phi model has 32 decoder heads, and we pruned 8 of them. We pruned decoder heads 21 to 29. And then after that, we also did a widthwise pruning on the embedding dimension of Phi. And now we have two different versions of the model. We have the depth pruned version, which is 2.8 billion parameters, and the width and depth, which is 1.8 billion parameters. And then after we did that pruning, we did a multi-stage healing to breathe some life back into the model and make it generate coherent text again. The first healing was a long healing of 45,000 steps and 15 billion tokens. And this recovers knowledge and basic coherence. And then we did a SFT or instruction fine-tuning on top of that. This is just one epoch on the OpenRes dataset, and this helps recover the alignment. The original paper, which we pulled this from, they only did a Q-LoRa healing, and we found that that wasn't enough to recover the model's underlying capabilities. So we are proposing this new recipe, you could call it, of healing to recover model coherence after pruning. And then I'll hand it to my colleague Yahya, and he'll talk about the fine tuning and then the on-device deployment.
Hi, my name is Yahya Sowti, work in the same group, Farris works, machine learning engineer for Mercedes-Benz research development. So the goal was to make sure, so the original, traditional voice assistant are very rule-based and just can able to answer to very basic questions. So our goal was that giving it some language understanding. Let's say saying that I have backache, so it was able to activate a massage in the seat. So that's why we also had to do fine tuning. At this step, we did fine tuning on synthetic data, which is a function calling data set. We generated a synthetic data set using like ChatGPT, other tools, which was specific to our functions, the functions available in the vehicle, mostly comfort functions. And then we fine-tune our model using LoRa or fine-tune it so that we give it also function calling capability. Making sure that we evaluated it on the data set in a way that making sure that it keeps its original chatting capability. Also, it has a new function calling capability. You can see it was able to get to 88% accuracy. Our goal was to get to like around 12 token per second, so that this function interaction with the user is more in real time. So you can see after pruning, making model more compressed, we were able to, from the base model, which is to 6 token per second, we were able to get it depth-wise and width-wise pruning, we were able to get to 11 token per second. One additional step that we did was quantization with 4-bit quantization. So for 2 steps, basically, two types of compression, pruning and also quantization. And with that, we were able to use runtime, Llama CPP on the vehicle. And this is tested. It was able to activate functions in vehicle as the user asks pretty complex questions, making it more interactive and more intuitive. Thank you so much.